In this video, we're going to discuss Newton's laws, which are the fundamental laws that underpin all the mechanics we're going to do this semester and next. Energy conservation, angular momentum, all those things can be derived from Newton's laws. Of course, you can start in the opposite end too and start with energy and energy conservation and then back out Newton's laws. That's also just a fine way of doing mechanics. Perhaps it's even more fundamental. But starting with Newton's laws works well for us, and you're already quite familiar with it, so we'll start here. So, there are three Newton's laws, and they are valid in an inertial reference frame. So the first law says that an object subject to a net force, or an object subject to no net force, moves at constant velocity. And Newton's second law says that if there's an external force acting on an object, then it accelerates. And the relation between the two is given by this formula. F equals ma, which we're going to write as mr double dot, because it's the second time derivative of position. And then we have the third law, which is that every force is part of a pair of forces. And where the two forces are equal and opposite. You're obviously very familiar with these, but they are very fundamental, so we'll go through them in some detail nonetheless. We'll focus first on the first two laws. Interestingly, it seems, when you look at it, like Newton's first law is really just a special case of Newton's second law. What it says is if the net force on an object is 0, that means that the acceleration is also 0, and vice versa. So that really is just a special case of this. The question then arises, why do you even have that as a separate law? Wouldn't it be just easier to talk about Newton's two laws, number 2 and number 3, and just strike number 1? Well, there are two reasons why we have Newton's first law as a separate law. The first one is really psychological. It's easy to take the Aristotelian view that for an object to have any velocity, there has to be force acting on it. And that's because we live in a world full of friction, so the natural or intuitive way of looking at forces is to say that if the force on an object is 0, then the velocity will eventually go to 0. And that's not true. That's because we have a tendency to neglect friction forces and forces that don't involve any actual effort on the part of anybody. And the second reason is more fundamental, and that has to do with the concept of frames. So I wrote here that in an inertial reference frame, that is a frame that doesn't accelerate, this is true. In particular, 1 and 2 is true. Newton's third law is true in any frame. So to see how this works with Newton's first law, let's consider a specific example. Let's say that we have an ice hockey player. There's an ice hockey game going on, and we have one player here. And he's just passed the puck toward a second player that's coming in this way. And over here is the opponent's goal. So a player from the opposing team now is sprinting to come in from the left here to cover the goal. Okay. So this puck here is moving relative to the ice by some velocity v puck, let's say. And this player is moving relative to the ice by some velocity capital V. This player over here is actually accelerating in order to be able to get in front of the goal in time by some acceleration a. And we can now identify with each of these three players a frame. So all of them have their own separate frames. So let's say that this first player here is stationary relative to the ice. So his frame is not moving relative to the ice. The second player here, he's moving with some velocity relative to the ice. So his frame is moving relative to the first player. And then we have this third player from the opposing team. His frame is then obviously accelerating. Now all players, all the observers, agree that there's no net external force on this puck. But they all use different ways of measuring the position of the puck. Right? So the player here in the S frame is measuring the position with this vector r. The player in the S prime frame is measuring the position of the puck with vector r prime. And the player in the S double prime frame is measuring the position of the puck with vector r double prime. Okay, but they're all referring to the same puck, but they are using different measures because they have different positions. Okay, and because they have different positions, they come up with different velocities for the puck. So in the S frame, this player S, will see the velocity of the puck as being v sub p. That's the velocity of the puck relative to the ice, because this guy is stationary relative to the ice. And that's a constant. Player S prime also sees r prime as a constant, but it's different constant. It's vp minus its own velocity, but that's a constant. So in these two cases, anyway, Newton's first law is valid. It seems clearly because there's no net force, and we have constant velocities. The player over here in frame S double prime, they will see that the acceleration of the puck is different from 0, which means that the velocity is not a constant. Even though this player, of course, agrees with the others that there's no net force on this puck. So in this case, Newton's first law is not valid. And we can resolve all of this by simply noting that if the S frame is inertial, then S prime is inertial because it's not accelerating with respect to S. S double prime, however, is accelerating, so it's not inertial. And that's why Newton's first law is not valid in this frame over here. There's, however, one small problem, and that has to do with this little f over here. This reasoning here that explains the observations is predicated on the fact that we know that the S frame is inertial. But the universe doesn't have a default frame. There's no master frame we can refer to and say this frame is inertial, and therefore any frame that is not accelerating with respect to that frame is also inertial. So the problem then is, how do we know that S is inertial in the first place? Well, we know that S is inertial because Newton's first law is valid in S. Because Newton's first law is valid in S, it also has to be valid in S prime and in S double prime. So really, Newton's first law is a way of picking out inertial frames. So Newton's first law defines inertial frames. So if Newton's first law is valid, then we know that Newton's second law is also valid. Then we can do some more interesting things. And that's the more fundamental reason why we have Newton's first and Newton's second law as separate things. So let's now look at Newton's second law in a little bit more detail. So Newton's second law says that if the net force has some value on an object, then that equals the mass of the object times the acceleration of that object. So in Cartesian coordinates, this is pretty easy to write out in component form. Because in Cartesian coordinates we have that r dot is of course equal to d dt of x hat plus y hat plus z hat, and that's equal to x dot x hat plus y dot y hat plus z dot z hat, and similarly then of course for the acceleration. And this works because these vectors are fixed, the unit vectors are fixed. They don't change in time because the system is not rotating. If it did, the frame would not be inertial. And it's the same at every point in space. That makes Newton's law easy to work with in Cartesian coordinates. It amounts to these three equations, namely that f sub x equals m x double dot, and the same thing for y and z. But we don't always work in Cartesian coordinates. Sometimes it's much more convenient to work in curvilinear coordinate systems. So in polar coordinates, things are more complicated. I'm going to restrict myself now to planar polar coordinates because that makes things simpler. But in polar coordinates, we know that the position vector is just r hat by definition. So if we now want to calculate in polar coordinates the velocity, that is d dt of r hat. So that's going to be equal to r dot r hat plus r hat dot. And this, as we've shown earlier, if you go back to the videos on vectors, frames, and coordinate systems, we know that this is actually not zero, because r hat does change with position. And we found earlier, in fact, that r hat dot equals phi dot phi hat, and also that phi hat dot, if we need that, is equal to phi dot minus phi dot r hat. So that means that this velocity here, if we write it out, that becomes equal to r dot r hat plus r phi dot phi hat. And we can calculate then the acceleration in the same way. And then inserting these things, we get which we then can rewrite like that. So if we now want to write out Newton's second law, we instead get, instead of the simple formula, we get that. And if you were to do this in spherical coordinates, it would obviously be even more complicated. So this is still Newton's second law. We haven't done anything special, but we're working in polar coordinates, and that makes things more complicated. In fact, the fact that this is complicated is going to be the motivation, or one of the motivations for doing Lagrangian mechanics, which is another way of doing mechanics that we will do later in the semester. I should note that this expression for the acceleration is true in general than in polar coordinates, but you've seen something similar previously. So let's examine, just to give you some way of orienting yourself, the special case of the radial acceleration equals 0. Well, not only the radial acceleration, but also the radial velocity. So both the radial velocity and the radial acceleration equals 0. So this is now circular motion. In that case, the acceleration just becomes like that, right? Because this term goes away and that term goes away. Now if you look here at phi dot, that's a change in the angle. That's really the same thing as the angular velocity. This is the angular acceleration. So we can write this as minus r omega squared r hat plus r alpha phi hat. So this is the tangential acceleration, which is proportional to the angular acceleration, which you should have seen in 2305. This is the centripetal acceleration, which is r omega squared, which you should be quite familiar with. So that's contained within this case. So in any case, we can see that Newton's second law is not always going to be as simple as this if we're working with curvilinear coordinates. We should also introduce momentum in this context. So the momentum p of an object is the mass times its velocity, which is the mass times r dot, obviously. So then we get that p dot equals m v dot, or ma, and that's the force. So this gives us this other alternative formulation of Newton's second law, which is that p dot equals f. This is actually Newton's original formulation of his second law. In some sense, it's more fundamental, and we will use this interchangeably with the other equation. Let's say a few words now about Newton's third law. Newton's third law applies to objects that are interacting with each other. Whenever there's a force, so this is object 1, this is object 2 here, there's going to be a force on object 1. It's going to be coming from object 2. All forces are the result of interactions. And in that case, object 2 experienced equal and opposite force from object 1. So Newton's third law simply says that F21 equals minus F12 in this particular case here. Okay, so all forces result from interaction. So to recognize when you have an interaction pair like this, we can make the following 3 points. So the forces in an interaction pair, they're equal and opposite. They result from a single interaction. And they act on different bodies. So specifically, if you have the case of, some object sitting on a table, let's say, you have an upwards normal force N, and we have a downwards force of gravity mg. They are equal and opposite, but they don't result from the same interaction because the normal force is a contact force, and the force of gravity is then a completely different force due to long-range interactions. And second, they act on different bodies, so this is not an interaction pair. Another way to recognize interaction pairs, like these two, is to see what happens if you take away one of the forces. If you take away one of the forces, then the other one should go away too. And so if you turn off the interaction between these two guys, then both of the two forces will go away. Here, if you take away the table, the normal force goes away, but the gravity does not. So this is not an interaction pair. Now, from Newton's third law, we can also easily derive momentum conservation. So let's add in a couple of additional forces here. This is the external force on particle 2. This is the external force on particle 1. So we know that then that the force on particle 1, the total force, is equal to F12 plus F1 external, and the total force on particle 2 is F21 plus F2 external. Those are the forces. Newton's second law says that P1 dot equals F1 and P2 dot equals F2. If we now consider the total momentum, and look at its time derivative, P dot, so the total momentum P is just the sum of P1 and P2. So the total time derivative of the total momentum then is P1 dot plus P2 dot. That's going to be F12 plus F21 plus the external forces. Now we know from Newton's third law that these two add up to 0 due to Newton's third law. So the only thing that remains is the external force. So P dot equals F external. So specifically that means that if there is no external force, that means that the momentum is a constant. So the momentum is conserved when there's no external force. In other words, the internal forces within a system don't matter. Because of Newton's third law, the internal forces between two particles in a system do not change its total momentum. And if we have a more complicated system consisting of more particles, we can easily extend this same way of thinking to larger systems. And we'll get the same conclusion that in order to change the momentum of an object or a system that consists of many particles, we have to apply an external force. And in the absence of that external force, then the momentum is conserved.